Hello everyone, and welcome back to our channel. Today, we're diving deep into the fascinating world of exploration geochemistry, specifically focusing on the chemical analysis methods that turn a simple rock or soil sample into a treasure map of valuable data. Before any fancy analysis can happen, the data must be cleaned and prepared. This involves rigorous quality assurance and quality control, along with special data transformations. These steps are crucial because they set the stage for high-precision chemical analysis, ensuring we get the most scientific and exploratory value out of every single sample. The choice of analytical method is critical. It depends entirely on which elements we're looking for, the detection limits we need, and the type of sample we're dealing with. So, let's get started on our journey through the modern geochemical laboratory. First, let's talk about sample decomposition. This is the essential first step. Before most instruments can even look at a sample, the solid material, be it rock, soil, or sediment, needs to be broken down. This process, called decomposition, liberates the elements we're interested in, converting the solid sample into a liquid solution. This solution is then ready for instruments like ICP-MS or ICP-AES. There are two main approaches to decomposition: total and partial. Total decomposition methods, also known as a strong attack, aim for the complete dissolution of everything in the sample. This is necessary when we need to know the absolute abundance of elements, especially major elements and things like high field strength elements and rare earth elements. One popular total decomposition technique is fusion. Here, samples are mixed with a chemical called a flux and heated to scorching temperatures, often around 1000 degrees Celsius. Lithium borate fusion is a common choice, especially when we're measuring major and minor elements with XRF or ICPAs. Fusion is powerful because it breaks down all minerals, releasing every element. It's particularly necessary for determining silicon, which would otherwise be lost if we used certain acids. Another method is sodium peroxide sinter, which is great for decomposing minerals that resist acids and other fluxes, and it works at lower temperatures, below 500 degrees Celsius. Finally, there are strong acid digestions. These often use a mixture containing hydrofluoric acid, or HF, because it's excellent at dissolving silicate materials. Sulfuric acid is often added because its high boiling point helps remove any leftover fluoride. These digestions are usually done in sealed Teflon containers to make sure we don't lose any volatile elements like chromium. On the other hand, we have partial decomposition methods, or a weak attack. These are more selective. Instead of dissolving the entire sample, they target specific parts. This is very common in exploration because we are often looking for signatures of mineralization rather than the total amount of an element. A classic example is the aqua regia digestion. This is a mixture of nitric and hydrochloric acids. It's highly oxidizing and specifically targets phases associated with mineralization, like sulfides. Aqua regia is famous for dissolving native gold, platinum, and palladium, as well as carbonates and arsenides. However, it won't touch very resistant minerals like zircon or cassiterite. Another partial method uses chelating agents, like EDTA. These are used to estimate loosely bound metals in soils, which can give us clues about how metals are moving through water in the environment. Now that our sample is in a solution, it's time for the main event: instrumental analysis. The workhorses of the modern exploration lab are plasma and X-ray based techniques. They are fast, accurate, and can measure many elements at once. Let's start with one of the most exciting tools available: inductively coupled plasma mass spectrometry, or ICP-MS. This is a game changer and is now widely used in labs everywhere. ICP-MS is primarily used for trace elements and rare earth elements. It can analyze almost every element in the periodic table. Its key advantage is its incredibly low detection limits, which can range from parts per million all the way down to parts per billion. The solutions from our sample digestion are introduced directly into the ICP-MS. For analyzing water samples and hydrogeochemical prospecting, Older methods often required pre-concentrating the trace metals, but modern ICP-MS is so sensitive that this step is often no longer needed. Next up is inductively coupled plasma atomic emission spectrometry, also known as ICP-AES or ICP-OES. This method is the go-to for determining major elements and trace elements that are present in higher concentrations, from weight percent down to tens of parts per million. Inside the instrument, an incredibly hot plasma, reaching temperatures of 6 to 7,000 Kelvin, efficiently vaporizes, atomizes, and excites the elements from our sample. This causes them to emit light at specific wavelengths, which is what we measure. A great thing about ICP-AES is that its calibration curves are linear over a huge range, meaning we can often measure major, minor, and trace components all at once without needing to dilute the sample. Samples are typically introduced as solutions, usually from a total digestion like lithium borate fusion. Then we have X-ray fluorescence, or XRF. This is a very common method that works directly on solid samples. The technique uses X-rays to excite the sample, which then emits its own characteristic secondary X-rays that we can measure. XRF is used for measuring major elements as well as many minor and trace elements in geological materials. For the highest accuracy in major element determination, the sample is often fused into a small glass bead. For trace elements, a pressed powder pellet is more common. A revolutionary development in this area is the handheld XRF, or PXRF. These portable analyzers allow geologists to get rapid, on-the-spot evaluations of element concentrations in rocks, soils, and drill cores. This provides immediate information that is crucial for making fast decisions right there in the field. Beyond these main workhorses, there are several specialized and complementary methods. These are used for elements that are difficult to analyze, are distributed unevenly in the sample, or are volatile. For precious metals like gold and the platinum group elements, the gold standard method is fire assaying. This ancient but effective process concentrates the noble metals from a large sample into a small lead button. This button is then heated in a process called cupellation, which leaves behind a tiny gold or silver bead. This bead can then be weighed, or it can be dissolved and analyzed with a highly sensitive technique like atomic absorption spectrometry or ICP-AES. For gold specifically, we can also use aqua regia digestion followed by ICP-MS analysis, which can detect gold down to about 0.2 parts per billion. Another method is the cyanide leach, which targets free gold and can achieve detection limits even below 1 part per billion by using very large samples. Atomic absorption spectrometry, or AAS, was a cornerstone of geochemical analysis for many years and is still used for specialized applications. Standard AAS is great for high concentration base metals. It can determine about 30 different elements from one solution, one at a time, using specific lamps for each element. For the element mercury, we use a special technique called cold vapor AAS. This takes advantage of the fact that mercury is a vapor at room temperature. We can strip the mercury vapor from a solution and measure it directly. Similarly, for elements like arsenic, selenium, and antimony, which form volatile hydrides, we use hydride generation AAS. This converts them into a gas, making them easy to measure. Finally, we have a suite of micro-analytical methods that give us incredible detail. Instrumental neutron activation analysis, or INAA, is a non-destructive solid source method that is highly accurate for many trace elements and rare earth elements. Laser ablation ICP-MS, or LICP-MS, uses a laser to vaporize a microscopic spot on a solid sample, which is then analyzed by an ICP-MS. Its real power is in creating detailed maps of element distribution within mineral grains or analyzing the composition of tiny fluid inclusions trapped inside crystals. We also use the scanning electron microscope, or SEM, and the electron microprobe. The SEM gives us high-resolution images of a sample's surface and texture. The electron microprobe provides compositional analysis of tiny, specific points on that surface. Before this type of microanalysis, samples are often set in epoxy, polished perfectly flat, and imaged with the SEM to reveal any zoning or cracks. This helps the analyst choose the best spots for analysis. So, we have all this amazing, high-quality chemical data. What now? The final and most important step is to extract the maximum amount of information from it. This is where data integration and statistical analysis come in. Geochemical anomalies are rarely just one element. They are usually multi-element signatures. We use statistical techniques like principal component analysis or factor analysis to group correlated elements into associations. These associations, or factors, are much easier to interpret than the raw data and can be linked directly to specific geological processes or types of mineralization. A crucial concept here is compositional data analysis. Geochemical data is compositional, meaning the values are relative and sum to a constant, like 100%. This can create statistical problems. To handle this correctly, we use a special transformation called the centered log ratio, or CLR. This allows us to use traditional statistical methods reliably, avoiding spurious correlations. Ultimately, all this work leads to mineral prospectivity mapping. The geochemical data is integrated with all other available information: geological maps, geophysical surveys, and remote sensing data to create a map that highlights the areas with the highest potential for mineral deposits. This process uses multi-criteria decision-making techniques to weigh all the evidence and delineate the most promising exploration targets. And finally, we use spatial modeling. Geochemical data points are interpolated to create continuous maps using methods like inverse distance weighting or more advanced geostatistical techniques like kriging. This is all done within a geographic information system, or GIS, allowing us to visualize anomalies, track dispersion patterns, and ultimately define precise targets for drilling. From the initial sample preparation to the final prospectivity map, each step in the chemical analysis process is designed to turn raw geological material into actionable intelligence. It's a powerful combination of chemistry, physics, and statistics that drives modern mineral exploration. Thank you so much for joining me on this detailed tour of geochemical analysis methods. I hope you found it informative and engaging. If you have any questions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content on the science of exploration. See you in the next video.